Hello everyone and welcome to the next webinar series. I'm Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are excited to dive into our today's webinar titled Integrating FRP Meshes in Concrete Construction, Principles, Application and Guideline. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may also use the question box to ask questions during the webinar, and our speaker will address them at the end of the presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the next webinar series. So let's begin with a brief description of today's webinar. This presentation will provide an insightful overview of FRP mesh solutions in concrete constructions aimed at professionals looking to integrate innovative materials into their projects. It will discuss various FRP mesh options, their unique characteristics and practical applications in both repair and new construction, supported by the real-world examples. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speakers. Our first speaker is Francisco Di Caso. He is a principal scientist at Department of Civil Engineering and Architectural Engineering, University of Miami. He serves as director of the Center for Integration of Composites into Infrastructure, CICI, and NSF Industry University Cooperative Research Center. It focuses on technology transfer, and Dr. Di Caso is a member of ACI committees 130, 135, 364, and 440, and also a co-chair of ASTM D3010, Composites for Civil Structures, which is actively developing new standards. His research focuses on resilient materials, structural integrated solutions for built environment, and the decarbonization of the concrete and cement industry towards carbon neutrality by 2050. Our second presenter is Hussein Rogani. He is a postdoctoral research associate at Texas A&M University. Hussein obtained his PhD from the University of Miami in structural engineering and structural materials under the supervision of Professor Antonio Nani. Hussein is a member of ACI, an associate member of ACI 440, a voting member of ACI 440G, and member of ACI 88. And our third presenter is Alvaro Ruiz Esperanza. He is a postdoctoral associate at University of Miami. Alvaro graduated with honors with a bachelor in civil engineering from the University of Basque Country, Spain, did a master's of science at University of Applied Science in Münster, Germany, and a PhD at University of Miami. He is an active member of ACI committees, and he's also an active member of ASTM D13 and D30 related to composite materials in infrastructure. So with no further delay, I request Alvaro to start his presentation.
Yes, thank you. Let's go ahead on the next slide. And again, thank you, Aparna, for that introduction, as well as all the attendees for joining us today. I think as we advance the field of composites and reinforcement in concrete structures, we're going to divide the presentation that I'm kicking off in 6 main parts. We want to look at the what, the why, and the how FRP meshes specifically are being implemented and developed in order to discover all the tools available for the engineers, as well as the specifiers and the contractors. Next slide. And then the remaining 3 parts will be specifically looking at different design methodologies that currently exist that will allow us to implement and transfer FRP meshes in the building infrastructure, in the building and the DOT infrastructure. And part of the work that we have completed, we conducted a pulse survey in order to understand how FRP meshes are currently being used in order to understand the key benefits from these aspects. And finishing with the summary and some updates on the work that is currently undergoing. I'll finish this introduction by saying that all the work presented will be published in a guide that Next will be making available. So we're very excited to be able to share this information through Next. And with that being said, I'm going to pass it on to my colleague Alvaro, who's going to start us with the what. Thank you.
Okay, thanks, Francisco, for the introduction. So let me get into the first point, right? Like, what are FRP meshes? So FRP meshes are composite materials made of resin and fibers. Fibers are the elements within the composite that takes the load and gives the stiffness, and then resin helps transfer those stresses within the fibers, but also protect them to give that durability that characterizes these materials. Among the fibers, the most commonly used fibers are glass, followed by basalt, carbon, and aramid. And among the resins, we have thermoset and thermoplastics, even though I would say that thermoplastics are more on the research and development side of it and within the FRP meshes, and thermoset are the ones that are mainly used by all the manufacturers. Vinyl ester and epoxy are two of the resins mainly used for long-term applications, but we also have other more inexpensive resins, which maybe they don't have that much durability as the first two, but are used in temporary applications, for example, polyesters, polyurethanes. So if we talk about the types of FRP meshes, of course, there are like a lot of types. A lot of manufacturers have their own techniques to create these FRP meshes. Within this work, we have created or characterized them within three different groups. The first one is grid type mesh. The second one is the wire type mesh, and the third one is the bar type mesh, which we have rollout and non-rollout. Within the grid type mesh is pretty similar to the wire type mesh, but have a smaller spacing among the horizontal and longitudinal axis, and we have larger spacings in the wire type meshes. For the bar type ones are FRP bars that mainly are created through pultrusion that are tied together to create these meshes. There are some times where we have the rollout, which is the bars are aligned in one direction, and then we have two different rollouts that are placed within the slab, for example, and they create this orthogonal reinforcement. And then there are some others that we directly have bars in both directions, and we have the mesh that we can place it directly. So let's get a little bit on the manufacturing of the FRP meshes. As you can imagine, like the different types of FRP meshes that I have presented have different types of manufacturing techniques. The first one that I'm going to talk about is the pultrusion. This is one of the main manufacturing technique used with FRPs, could be meshes or bars. In fact, this type of linear manufacturing technique, it's where you have all your fibers on one side of the line and you pull them through. That's why it's called pultrusion, because there is a pulling force that it pulls all those fibers. It dives them through a resin bath, and after going through a die that gives the size and shape of the element, it goes through an oven where the resin is cured. The product of this technique is a longitudinal bar that, as I mentioned afterwards, they can be assembled to create the FRP meshes. So that this is the pultrusion. Another technique that it's used is the weaving technique. In this case, the product is not a single FRP bar that afterwards you assemble. In this case, throughout the production process, the two directions are being manufactured. So you have the longitudinal, but also the transverse manufactured at the same time, creating the mesh directly. There are also some other alternative techniques. A lot of these techniques come from the textile industry. but are also used by some manufacturers of FRP meshes, for example, the knitting, also the laminating, the welding or bonding, the additive manufacturing, and this is more recent, but I mean, there's a lot of development going on this topic. Then we have molding, and of course, these hybrid techniques where they combine some of these manufacturing techniques. Here, the last slide from this section, just to let you know that there's a lot of, even though for a lot of people it's relatively new, this FRP mesh, it's been around for a long time. There are big and serious manufacturers around the world producing this material. Here are some of them. And in fact, we're going to have one of the manufacturers join us today to give the manufacturer's perspective a little bit later in the presentation. So without further ado, Hussein, if you want to keep going from here.
Okay, thank you, Alvaro, and thank you everybody for joining this meeting. So now we're going to talk about the why. So why we're using FRP materials, and more specifically, why we're using FRP meshes. So there are compelling reasons for the use of FRP in concrete applications. So after all these presentations from the ACI Next and the other presentations that we have seen in the conference, I mean, in the ACI convention, so I think most of us are familiar with those key attributes of the FRP, so why we're using them in concrete. So to remind you, like material durability, the corrosion resistance, the lightweight of the material, the high tensile strength of the material in comparison to steel, sustainability properties, electrical and thermal non-conductivity. These are the main key attributes of the FRP and why we need to use it in concrete in specific applications. In terms of FRP meshes, in addition to these benefits, there are some more benefits. So one of them that I want to mention is the rolling capability, which make it much easier in terms of installation and also the transportation of the material, so you can easily transport it. And the other thing is for example, the memory feature of the material. So after rolling, or if you like step on the material, so you do not deform it, so you can use it easily after de-rolling it. And also, like what I mentioned about the stepping on the material, because one of the main applications of this material in my mind is the use of this material as shrinkage and temperature reinforcement in a slab on ground. So in a slab on ground, it's hard to not step on the reinforcement. So when you're using like conventional steel, like a steel welded wire mesh, you can easily deform the material during the casting, because the workers are going to work there. They want to like cast the concrete. They do not see what's going on under the concrete. They may step on the mesh and they will deform it. So the use of FRP can reduce those kind of deformation, and that's another specific feature about this material. So here you can see how the material arrives to the site if you order them from one of these companies. So you can see them in roll, and also you can see the other one, like you can see the mesh layout. The mesh layout itself is also something that can enhance the productivity. So they can easily implement the material. They don't need to like tie it at the site. So that's another thing that can enhance the productivity and the speed of the construction. So here I want to remind you about some of the mechanical properties of this material and the differences with the conventional steel. So you can see the stress-strain curves of steel in the left side, and then glass fiber reinforced polymer and the carbon fiber reinforced polymer in the right. So this material is made of fibers embedded in polymer matrix, as Alvaro mentioned in previous slides. So it has generally higher tensile strength in comparison to steel, but it depends on the diameter of the bar or the mesh, and also it depends on the type of the fibers. It has lower modulus of elasticity, so it means lower stiffness. So you may have some sort of different behaviors that you have to take it into account before using it in your project. So it has a lower density, so it has lower weight, so it can make the transportation easier, and also it's linear elastic. It has a linear elastic behavior, so the failure is going to be brittle comparison to a steel that it's going to provide you some. It's going to provide you ductility, and it has a ductile failure. So these are the main differences that you have to keep in mind. So there are some different type of testings for this material, like the constituent testings on the fiber and on the resin, and also some testing that they are for the bar types and also for the mesh types. So we talk about some of those differences later, like the physical properties, the same as the rebars, cross-sectional area, density of the material, moisture absorption, fiber content, like software for durability, software physical testing, and the mechanical testing, again, like for example, the tensile strengths, the bond strengths, these are like the concept is the same as the bars, the same for the meshes, but there's some specific tests like shear strengths or the shrinkage cracking that they are mainly for the grid types and the mesh types. So here I want to spend some time on the ICCES and the acceptance criteria. So ICCES is the International Code Council evaluation service that they publish the acceptance criteria. So that the acceptance criteria provide guidelines for evaluating a new material like a building product, components, or methods, to ensure they meet the requirements of the existing building codes. So later, these acceptance criteria are used to issue the evaluation reports that later we mention one of them, which verify the compliance of a material or company with the applicable codes and standards. So this specific acceptance criteria is for the FRP bars and meshes for internal reinforcement of non-structural concrete members, for example, non-structural slabs on ground, that you use the material as shrinkage and temperature control reinforcement. This document covers the material specifications, mechanical properties, durability testing, and quality control. So here are the list of the tests. If you're familiar with the ASTM D7957 or the 8505, most of these tests are the same between the bars, the regular bars that you use like in structural applications, and also the smaller bar diameter that you can use them as the mesh or the grid types. So many of these tests are the same. For example, I don't know, the fiber content test, mean glass transition temperature, I don't know, like the moisture absorption, tensile test, I don't know, the tensile modulus of elasticity. These things are the same, like in terms of the standards that we use to determine them. There might be some difference because of the type of the material in terms of like how to conduct the test, but the concept is the same. But there are like 3 specific tests that they're just for the meshes and the grid types. So you can see one in the physical properties testing. Like it's the actually that is not a test. Sorry, it's a variation in diameter is different. So it's you have to go to the section 416 of the AC 521 to determine those permissible variation in the diameter. And in terms of mechanical properties testing, there are 2 specific tests that they're just for the meshes and the grids, which is the mean shear strength of the mesh intersection. So you don't have it in the bars, right? So there's an intersection that you have to determine the shear strength. And there is the shrinkage cracking, which is developed based on the ASTM D1579, which is for FRC. So actually we worked on this quite a lot in University of Miami to develop a test method that we can use it for the FRP meshes and the bars to control the shrinkage cracking. So here is an example of an evaluation report issued by the ICCES, International Code Council Evaluation Service, which is for the binary composite. They are the first that they got this evaluation report. This report shows the compliance with the IBC, International Building Code, IRC, International Residential Code, and also the Abu Dhabi International Building Code, which is ADIBC. So you can see this, I mean, we just have 2 pages of this report here. It covers the design and installation, the condition of use. You can later go and take a look at this report. And here are 2 examples of the specifications and qualification. The 2 examples of the manufacturer specification that we have. If you check all these manufacturer specifications, like different companies that they have these meshes, you can see that their type of the report is different. There are some differences in the reports, especially even sometimes in the properties that they're reporting. So which highlights the need to standardize all these reports and the manufacturer specification, which is a real need. Hopefully this guideline that we develop can make that easier. and hopefully later, like other standards that they're going to come out soon, hopefully. So here, very quick on other specifications and qualifications. They're not directly related just to FRP meshes. They're like more general, mainly for FRP boards, the ASTM D7957 and the D8505. So I think you're familiar with this. ACI specifications, 440.1R, 440.3.7.9, CSA specifications, S808. Later, we also talk about the S806 and the ISO specifications. So here, I will give the floor back to Dr. DeCasso, and hopefully later we will talk about the methodology.
Thank you, Hussein. And the main thing that we want to explore now is in terms of the how. We understand the benefits, we understand how FRP meshes have been used, and the most important thing that I'd like you to remember today is that you're not the first using it. You probably won't be the last using it either. So I think that wary of applications and understanding if I can go ahead and do it because maybe I'm the first one, that's not the case. So let's go ahead and explore how FRP meshes have been used. And as we've already gathered from the explanations, there are many applications, and we want to divide the applications into these three main areas that we've observed. There's the repair and strengthening, primarily on existing structures, the new construction, and we can see a couple of slabs and grades. But we've also discovered that FRP has found its way in multiple specialty applications as the guides and codes maybe are more flexible in that approach. And we've seen that in this specialty applications, the growth of FRP meshes has found its way because there's less resistance for adoption. So we find that this has provided an opportunity and a window to observe the potential growth that FRP meshes have in concrete construction. Next slide. Let's first start with some of the existing structures. What we see on this slide is the repair of an existing bridge, where in this case, a wire mesh with a 2 by 2 inch spacing was used. The mesh primarily resulted in the savings of the parent material. The repair material that was used only resulted in a 40 millimeter inch thickness. If we compare this to the equivalent amount of material that a traditional steel wire mesh would have been, this would have been up to 70 millimeters thickness. So we're talking about a significant amount of savings on the parent material due to the adoption of the FRP mesh. In addition to the easiness of applying it, of cutting it, and following the shape of the bridge. Another example on how FRP meshes have been used on existing structures is more applicable on what we might refer as historic structures. One of the main aspects of historic structures is the ability to remove any repair material that has been done in the future in case there's new technologies, and primarily to preserve the original structure in order to avoid potential damage through polymeric resins that would bond and alter the parent material, the parent structure. To that end, cementitious-based repair systems typically find their way in the repair of historic structures, as there's more compatibility with the substrate, and there's the ability, again, to go back in the future and repair as needed. In this case, the concrete FRP mesh was used in the restoration of this historic bandshell in the state of Louisiana. And it's important to see that the ability to fold and curve and follow the curvature of the existing dome was feasible. And once again, the amount of material thickness that was installed in an existing structure that might have limited capacity was another of the benefits of using this composite material. An area where we're seeing primarily a lot of research development in line with the ability to save the bulk material that we see in pavements is using FRP meshes in between pavement layers in order to reduce the amount of material that is needed in the construction, on the overall construction of these pavements. While this has primarily been at a research level, the results so far show that there's a significant benefit And in this case, obviously, the use of FRP meshes is primarily guided by the use of its corrosion-resistant nature. And that coupled with the ability to reduce the material in order to have an overall resistant pavement structure. With this, I want to invite Igor Litvinov, who's the business development from Benevere, to really give a perspective on how FRP meshes are being used on projects and give us an insight on a couple of projects that provide benefits, so that you see that this is not purely academic, but there's a really practical aspect to it. Igor, whenever you're ready.
Dr. De Casso, thank you so much for the introduction. Okay, 8 years ago, we were 3,000 miles away from the job site. It was quite a challenging project. First project when we really used FRP mesh in a shotcrete application. We had two objects there. First, how can we deliver our mesh to the job site, which is again 3,000 miles away? And next challenge was, how can we attach mesh to the existing structure and be completely non-metallic? You can see the small piece of steel wire attaching mesh to the anchor. However, years later, we came up with a new design of the anchor, so never stop in development. Another shotcrete application was in California a couple of years ago. The benefits delivered by using FRP is ease of installation, the workability, and this product has no memory, so it flattens out. And this is one of the most recent applications for the slab on ground reinforcement. Key Marathon is located down in Florida Keys, where corrosion is a big issue. So the material of choice was FRP reinforcement. It was 12,000 square feet of new slab that's been poured, and all reinforcements, the installation of entire reinforcement took less than 2 hours and just 2 men. That's another project in Florida. The concrete driveway reinforced with W2.9 mesh. It was just, again, 2 people to install all the reinforcement. Very easy to work with. Yep, it's just nearby. It's Boynton Beach, several miles away from where we are now. And again, the flat work application, we used mesh for reinforcement of slab on ground, which is actually the sidewalk. And I want to stop on this slide for a second and just mentally go back 8 years ago when we had a challenge of how can we deliver this pretty significant amount of mesh 3,000 miles away from a place it's been manufactured. So what's the difference now between 2018 or 2017 and 2024? And the biggest difference now is that FRP mesh is actually available. There are several manufacturers, many supply houses, many lumber yards already carry this type of product. So it's physically available, and as Dr. De Casso mentioned before, you will not be first using this material. Thank you so much, and Dr. De Casso, I'm yielding the floor back.
Thank you, Igor. And actually, before we go back, let's go back to the driveway on the slab on grade. And I want to reiterate the key items in terms of the speed of construction and the increase in productivity. But when we look at residential construction, this really represents a key concrete construction industry application for FRP meshes. In addition to providing the reinforcement needed for the expected vehicular loading, it really presents an opportunity for growth when combining FRP mesh with pervious pavements. Pervious pavements can reduce the volume of stormwater runoff and peak discharge rates. This is clearly in South Florida a big challenge for many counties and states. And they also help reestablish the natural hydraulic balance by slowly releasing the precipitation into the ground. So beyond the FRP mesh productivity and savings and transportation, it is important that it's enabling key environmental aspects that we are not able to provide with traditional materials. We go into the sidewalks. In the same way with the driveways, pervious sidewalks, in addition to helping the stormwater management, can reduce the concentration of pollutants in stormwater, which we typically see in residential areas. And pollutants can be trapped in pavements from a physical, a chemical, and biological point of view. In addition, when we talk about water quality of the rainwater by capturing those pollutants, whereby the pavement or the pervious pavement acts as a filter to those pollutants, the overall environmental impact can significantly improve local communities from that point of view. And that obviously translates in economic benefits that might be not directly associated with the construction or to the owner of that property, but to the entire community. Let's go on to additional examples on how FRP meshes are used. This precast floor slab application shows a carbon FRP mesh that are being used for parking, for slabs on parking garages. One of the main reasons in this aspect, again, comes back to providing that reduced bulk material, reducing the amount of material, generating a thinner and lighter weight panel that obviously creates less loading onto the existing structure, as well as the high quality and control ability of placing the material in the right thickness of the material where it is needed. As we go through more precast applications, this will look at a different reinforcement application. In the case of these precast wall panels, the FRP mesh is primarily used in order to connect the external and internal widths of the materials between each other in order to ensure high insulated capacity. And obviously, being non-metallic, it does not provide a cold bridge between those two aspects, and therefore provides the ability of creating a high efficiency insulated panels, which in this case were being used at a hotel, at a proximity hotel in North Carolina. When we look at specialty applications, I wanted to show two more examples on how FRP meshes are used on items that we might not think are critical, but represent also a significant application. Here we see in-ground swimming pools, and the primary benefit here has to do with the electrical current and not having to ground pools. The entire shell of the pool that is traditionally referred to has to be grounded due to electrical conductance. In this case, the FRP meshes are non-metallic, do not conduct the electricity, and therefore grounding in-ground swimming pools is not needed. That provides an additional saving of materials, but again, we also see the benefits of reduced shell thickness, as well as the speed of construction and productivity increase. And with the last example on a specialty application, I wanted to share one that actually this project was constructed here underneath the existing Interstate 95 in the downtown Miami area. This is a skate park that was provided through FDOT funding and Miami-Dade County. And one of the reasons why FRP mesh was used was, again, the ability to look at environmental alternatives. So this was considered as part of the project. The ability to shape and obtain this, quirky shapes for a specific application of a skate park that would allow to bend and provide continuous reinforcement without having to bend, and obviously the speed of production, the speed of construction, and the productivity in the construction. So all those aspects led to this park that was completed underneath A95. And adding that obviously the transportation of these materials and being able to not have heavy cranes to unload and reload reinforcement materials. These were secondary benefits that the contractor in this project realized he was able to achieve by the use of a lighter weight material and non-metallic material. And with that being said, we're going to switch on to the fourth part of this presentation, and I'll pass it on to Hussein. Hussein, when you're ready.
Thank you, Dr. Picasso. So in this section, I'm going to talk about the design methodologies, like the different specifications we have, specifically in North America, and also we mentioned some of them internationally. So first, I'm going to start with the ACI 440.1R of 2015. So one could ask why you don't talk about the ACI 440.1122. Actually, like most of the applications we are mentioning here, especially not most of them, but one of the main application is the use of this material as non-structural in non-structural applications, as a non-structural reinforcement for shrinkage and temperature. So one thing about the 440.1R, 440.1122 is that this document does not cover the slab on ground that is non-structural. So it doesn't cover the non-structural slab on ground. And for this type of application, it refers you to the ACI 360, which is for the slab on ground with the steel reinforcement, to use it in combination with the ACI 440.1R to do the design for the GFRP. So that's why we go to ACI 440 first, that like the 1R first, like in two sections, in two parts of these documents, we have equations and guidelines for the use of FRP as shrinkage and temperature reinforcement. The first is in chapter 9, so which discusses the amount of reinforcement you need to control the shrinkage and temperature. So it's basically just use the ratio between the tensile strength and the modulus of elasticity of your GFRP in comparison to steel to come up with new numbers. And also it provides the maximum spacing. Like in all those documents that I have observed, like in North America, they have the same maximum spacing of 3T or 12 inches, whichever is the minimum. I mean, 3 times the thickness of the slab, or 12 inches. So as I mentioned, two parts of this ACI 440 mentioned the related applications that we are talking about. Like one was the shrinkage and temperature, and the other one is the construction of slab on ground. So in this appendix, the document mentioned the construction of plain concrete slab on ground, and also slabs that have reinforcement to again address the temperature and shrinkage. So it provided a formula to determine the amount of reinforcement, which is based on this formula, like the mu LW over 2 0.0012 EF. You have Young modulus of the modulus of elasticity of the FRP that you're using. You have the mu, which is the coefficient of the subgrade, which is related to your job site. The L is the joint spacing in that slab on ground, and the W is the dead weight of your slab per square feet. So you can use this formula to determine the amount of reinforcement you need, or for example, when you have a specific grid type or a mesh type that's provided by a company that it has fixed spacing. So you cannot really play with the reinforcement ratio or the area of the reinforcement. You can have that as a constant value and determine the L, which is your joint spacing. And instead of like playing with the reinforcement ratio, you can change your joint spacing. So the other document that mentioned specified the minimum requirements for FRP reinforcement is the CSA S806. So it provided another formula to determine the minimum amount of reinforcement that I would say can use it for the minimum reinforcement for the shrinkage. Again, the same maximum spacing, like 3 thickness of the slab or 12 inches, whichever is the minimum. Also, the H2 LRFT in section 2.9.6 mentioned the shrinkage and temperature reinforcement. So basically, it's the first formula, like 0.0018 multiplied by whatever. So if you lump the constant numbers together, you can get the second formula. Actually, you have to determine the first value and choose the maximum, and this maximum should be less than 0.0036. So it used the design tensile strengths instead of the tensile strengths provided by the company. So the FFT is your design strengths, which you have to take into account the environmental factor, so which is CE, which is your environmental reduction factor, and also the same maximum spacing of 3 thickness of the slab and 12 inches. And here is another document that is recently published by ACI Next, MNL 623. So it's recommended practice guidelines for FRP bars in pre-engineered projects. So these pre-engineered projects are the one that we can, I would say, easily use FRP meshes. So because of the type of those applications and the way this document provided guidelines for this kind of design. So later we can discuss it. So this document actually is providing how to work with the material in those applications, and also details some key considerations for where to use this GFRP material, types of the GFRP material that they are available for these applications, and how to plan for installation. It provides also the key attributes. So the document provides some prescriptive design guidelines in terms of tables for some common applications, such as slab on ground or residential foundation walls. So the tables are similar to ACI 332, which is the code requirements for residential construction and commentary. So if you're familiar with the document, so you know what are those tables, and maybe it makes it easier for you to use them. So these tables are meant to allow the contractors to understand how to select the appropriate size of the material, the location, the spacing of the GFRP for a specific project, and compare it to steel. For example, in table 4.2, you can see that the table can help you easily determine the maximum spacing of GFRP bars for slab on ground. For example, if you're using number 3 bars, so what should be your spacing in each direction based on your slab thickness. And the next slide was for the basement walls, almost same thing. So it provides you with the spacing and information that you need for a specific type of the wall, depending on the wall thickness, your concrete strengths, the Young modulus of the FRP reinforcement that you're going to use. So it provides you some sort of prescriptive guidelines in form of tables that can make the design and choose of material very easy for the contractors. So very quick on international design methodologies. So I'm not gonna spend too much time here. Just we mentioned them: the Chinese standard code for FRP bars in hydraulic engineering, the European standards, the annex at Eurocode EN 1992, the Australian standards AS 5204, Japanese standards, Indian standards, which is a specification for the use of solid round GFRP bars. And here I can give the floor back to Alvaro. Can continue from here.
Okay, Dr. De Caso, you wanted to make a comment before I jump into industry?
Thank you. Yeah, I wanted to go back to the next document for pre-engineered applications. I wanted to highlight that the tables that we saw there primarily reference the use of FRP bars, which are then placed on a mesh approach with a given spacing. Should be important to highlight that, as we saw earlier on the presentation, manufacturers of FRP meshes, these are the wire type meshes versus the bar type meshes. Within their specifications, they will also provide similar tables where they recommend the different thicknesses of the slabs or the concrete elements to be reinforced with the wire type meshes, as well as the grid type meshes. So while this document, which is available to the public and in many cases uses number 3 bars, which are used in the FRP mesh type applications, the restriction of this document is only for the FRP type meshes. And we encourage individuals that are interested in using FRP meshes to also contact the manufacturers and ask for their specifications to find out the recommendations on the different concrete strengths and thicknesses when using meshes that are not FRP meshes. And with that, I'll give it to you. Thank you.
Okay, so then at some point as we were going through this project, we thought, like, what does the industry think and feel about FRP meshes? So we decided to create a survey with 24 questions and share it among contractors, engineers, end users, the different industry stakeholders that would, one way or another, use the FRP meshes. We got about 30 people or 30 companies respond. Among them, there were people from academia, from the manufacturing side of it, contractors, consultants. And we did not only share this survey among stakeholders in the US, but we also shared it internationally. We distributed it among Europe, Saudi Arabia, also in Thailand and other countries, to get a more international perspective and not only focus on the US. We know that this is the main market for FRP meshes so far, but there's also quite a little bit of use internationally. So I'm going to share some of the results in the next couple of slides. So we saw that predominantly the use of FRP meshes, as Dr. De Caso and Dr. Rogani mentioned, is both in new construction but also in renovations. And there's a lot of flat work being done with FRP meshes, a lot of slabs on ground, bridge decks, but also some precast work, as Dr. De Caso mentioned in the case studies. In terms of the benefits that the industry sees, the labor productivity and the acceleration of the construction time were some of the main attributes, together with improving worker safety. We know that nowadays the lack of labor, it's a big deal. So using materials that enhance that productivity and make the workspace safer, it's a huge benefit for the different stakeholders of the FRP mesh industry. However, of course, they saw some challenges. There were some participants that saw a tendency to float. This is something that I personally haven't seen it, but apparently there's been some cases where since the FRP mesh is lightweight and 1/4 of the weight of steel, apparently there are some cases that it tends to float, but this is easily resolvable by tying the mesh, but this is something that we found out. And the cost, the cost varies a lot. It varies a lot based on the materials that are used, the raw materials. Are we using like a fiber or another type of fiber, one resin or another? But it's true that in some cases the cost has been higher, the cost of the material itself, not talking about the offsets of maybe using less amount of material, as Dr. De Caso mentioned, or using less people to work on it, that you can have a lot of savings over there, but the material itself, sometimes it's more expensive, not always though. So it depends. In terms of versatility of the material, the industry saw that the FRP mesh could be adaptable across like a variety of construction scenarios, which that flexibility helps a lot. In terms of standards and certifications, and coming back a little bit to what Dr. Rogani mentioned, the ACI 440.11, the ACI 440.1R, and the ASTM standards are pretty known among the different professionals. It's true that there might be some other design guides and references that could be very helpful, that maybe there's not that much, people don't know about it. I know Next, for example, is doing a lot of efforts to make that awareness. In terms of procurement factors, again, coming back to the cost and quality and understanding that cost implications, but also the savings that you could get both on concrete and labor are something that some industry stakeholders maybe don't or haven't experienced it and haven't gone through the entire process, so they may not know about it. So making people aware of those savings, I think it will boost the use of FRP meshes. In terms of environmental impact, there's a significant appreciation of the reduced carbon footprint. We know that nowadays the global warming and the carbon footprint topic, it's a big deal. So using materials that have a reduced carbon footprint, it's a great initiative. And finally, last point, recyclability. We saw that the industry didn't feel it was a big deal, that the recyclability of FRP meshes right now, it's not fully understood in the sense that there's a big benefit that you can crush your FRP with the concrete and use as recycled aggregate, and you don't need to differentiate the reinforcement and concrete as you need to do with steel. So that's a way of recycling. But using thermoset resins, it's tough to get the fibers and resin back. So there's a little bit of work having to be done in the recyclability. So yeah, that was the last point. And with that, I'm gonna yield the floor to Dr. De Caso to conclude our presentation with the summary and the next steps.
Thank you, Dr. Rees. And so let's summarize what we've learned so far in the last hour without going into the detail of the specific ones, as you can read on your slides. I think we are seeing that FRP meshes are enabling concrete construction, primarily focusing on the reduction of labor costs, which increases the speed of construction and the productivity. We do have test standards and design methods, as well as design aids, which are helping advance the industry. And while corrosion resistance was initially believed a key indicator, it is not the primary benefit for the users, in this case, the contractors that are using it, where if they are able to, they will make the switch from traditional metallic reinforcement to non-metallic FRP meshes. However, they need the buy-in of the other stakeholders, such as the owners and the engineers, in order to do it. And for that, again, we revert to the standards that exist and enable them to leverage on that. Next slide. In terms of what is next and how do we take and grow the market, we see that the enhancement comes from education. We also recognize that education beyond the technical aspects that we've reviewed in terms of the material properties, the design tools that are out there, and potential case studies in application, it is important to speak to the non-technical stakeholders in terms of the owners and the architects and ensure they can see the wider benefits of the implementation of FRP materials, especially the meshes. This goes beyond the mechanical properties, the non-metallic, the efficient construction, and leverages onto the environmental enabling aspects that FRP meshes can provide. And to that extent, integrating the necessary tools is critical. We see that many manufacturers are developing their own tables so that it becomes very easy to implement. And that's why the examples that we saw on residential constructions show a significant application of the market, as within the international, the residential building code, it allows an easiness to implement FRP meshes. Next slide. And we've already taken action. Here at the University of Miami, we've taken action to develop an ASTM standard that specifies FRP meshes, therefore enabling the procurement and the specification in bid documents for concrete construction. Currently, this is a working document involving several manufacturers that will define FRP meshes for concrete reinforcement. And we hope that with this key element, this will be the binding document between the different stakeholders that will help enhance and improve the implementation of FRP meshes in our concrete infrastructure. And with that, I thank everybody for their time and the participation, and we can switch questions as needed. Thank you.
Great. Thank you, Francisco and Alvaro and Hussein, for this outstanding presentation. You covered most of the aspects, like right from standard codes, application, and special thanks to Igor to presenting the manufacturer perspective. It's really important to have some real world experiences. Thank you so much. So most of the question answers we have is like kind of answered, but I'll just go through them quickly. What are some of the best practices for integrating FRP meshes with existing concrete construction methods to ensure structural integrity and efficiency?
I think the answer is that not much needs to be changed. You can use the same concrete mix, you can see the same concrete processes and procedures, but it's important that you're not just replacing one steel reinforcement equivalent to FRP mesh. And I think that's where sometimes we see the trouble might come, and you might see unnecessary cracking that you wouldn't expect. So you cannot remove a number 3 bar steel and replace it with a number 3 FRP bar mesh. And similarly, an electrowelded wire mesh. I think for that, you need to consult the design meshes, but not much needs to be changed. And the next part of my answer would be that if you are able to change the mix design, then you can enhance the savings that come with the implementation and FRP non-metallic materials by removing any admixtures that are used to passivate the steel. You might be potentially reducing your concrete cover, especially for external applications, and therefore reducing their overall cost related to the concrete. So I think you can do a lot of changes that help cost and productivity and reduction of materials. But if you're not sure, don't change anything. Make sure that you replace the material in the way that either the table or the manufacturer allows, so that you can get that first experience.
Yeah, as you talked about the cost, so I'm going to take our next question, which is related to the cost. The question is, what is the cost difference between steel reinforcement and FRP reinforcement?
Yeah, right. You want to take that? Yeah, go for it.
I'll take that one, or I don't know if Igor wants to talk about it from the manufacturing perspective, as you're gonna go. Do you want to take that one, Igor?
In 30 seconds.
Yes, even less. In the several states where we already have a distribution, the cost of, for instance, W1.4 mesh in the form of roll 5 foot wide by 150 feet long is equal or 10% more than the steel equivalent, which would be W1.4 mesh in 5 by 150 roll. So we're talking in a stage where we already have a distribution as a manufacturer, we see pretty much the same price with a steel reinforcement.
Okay, yeah.
And again, I would revert to, don't focus on the price and the cost of the material, the project delivery. Because a lot of the savings are going to come from savings of labor, savings on material cost of the parent material. That's where you're going to see the primary savings.
Wonderful. So our next question is, what are the current industry standards and regulations governing the use of FRP mesh in concrete construction, and are there any upcoming changes we should be aware of?
Hussein, you want to take that?
Yeah.
Sorry, can you again say? I didn't get the.
Yeah, so it's more about like standards and regulations. What are the current industry standards and regulations governing the use of FRP meshes in concrete construction, and are there any upcoming changes we should be aware of?
Actually, I think one of the reasons that we started this project and the ACI next asked for this proposal to work on this topic was the lack of standardization and having specifications on this topic. So we have some limited documents that we can use. For example, we have the acceptance criteria that help us to find a way to characterize the material, come up with the minimum requirements from the material perspective. But still we need, like, for example, we need some good standards, as Dr. De Caso mentioned, like to come up with ASTM. It's the ASTM that is specifically for the meshes, not for the bars. And also we need to see the name of the meshes and the grids in the build. I mean, in the other documents that we have by the ACI. For example, now you may not see this specifically in the ACI 44T, that how you can use this material if you have a slab on ground that is in a non-structural application. So I think we still need more, that hopefully it's going to come, but for now, I think we have just some limited documents that you can use. For example, like the documents by...
And I would revert, if I may add, Hussein, to your answer, that within the International Building Code, wherever the International Building Code acceptance criteria 521 provides the necessary building code requirements. And then 440.1R, even though it's 2015 version, which is currently under ballot, also provides design guidelines, in addition to what the manufacturers will be able to provide, that many times are developed through experimental validation.
Yeah, I would just like to add that, yeah, the next funded and the mesh guideline, which is prepared by Francisco and team, like University of Miami, we will be publishing it shortly on Next website, and it will be available for reference and also as a guide how to use FRP mesh. And we will also have the manufacturer data as an appendix, so that it will provide assistance for whoever is going to use it. Great. I think I'll take a last questions. This will be our last question. Can you discuss the environmental impact of using FRP meshes compared to traditional steel reinforcement, particularly in terms of sustainability and life cycle performance?
You want me to take this one? So, I mean, I think whenever we talk about the environmental benefits, we cannot just focus on the material itself. So it's similar to what when we were discussing the cost, right? So the material itself, there's a lot of life cycle analysis done. I mean, we have a material that is more durable. So, I mean, a lot of your environmental impacts are tied to the durability of your material. So you have better results than, in a lot of the cases, than traditional materials like steel. The thing is that whenever you get a more holistic view of the project, then those reductions could be way more significant, because all of a sudden you have a reinforcement that it's durable and non-corrosive. When we know that concrete, one of the main the main tasks that concrete has together with the reinforcement is to protect it and to create that passive layer so that the steel reinforcement doesn't corrode. All of a sudden, that extra concrete that you need to keep the reinforcement from not corroding, you don't need it. So you may use less cover, less reinforcement, but not only less material, which not every time is possible. You can use a concrete that it's less protective. When we call less protective, means a lot of additives are used now in concretes in very aggressive environments to gain more protection towards steel, that we can just take them out of the equation. Those chemicals can be reduced, which reduces the environmental impact significantly, but also the cost. So there are a lot of studies for this life cycle analysis, and they are out there. And generally speaking, the savings are significant, I would say.
Yeah, wonderful. Thank you so much. I think this is the end of our question answer session, and all the speakers, thank you so much for your input and sharing your expertise with us.
Thank you very much. It's been a pleasure.
Thank you.
Thank you very much. Thank you.
Yeah, so before we go, I have few announcements. So like every year, Next has opened its call for ideas for 2025 funding. So please submit your ideas by May 31st. The submission guidelines and the fillable submission form can be found on Next website, www.nonmetallic.org, and then go to Next projects. You will get a fillable form, and also there will be a copy of PDF to be downloaded and filled out. If you have any questions, please reach out to us. This is a list of upcoming webinars at ACI University. Please visit aciuniversity.com to register. And thank you so much to all the attendees for attending this webinar. And we will see you next time for our next webinar. Thank you so much. Bye-bye.